Hello, listeners. Welcome to episode 25 of The Circuit. I am Ben Bajarin.
Greetings, programs. I'm Jay Goldberg.
A quarter of 100 episodes, Jay. 25. We're at a 25 episode milestone.
All right, good for us.
Who'd have thought there'd be so much interest in semiconductors? So appreciate all the kind words everybody sends us and messages we get. But today we want to focus on this idea of the underlying dynamics and or challenges, competition, or challenges, constraints, and even competition in taking the semiconductor industry from, call it $600 billion a year to $1 trillion, which is where most people have said, hey, it's going to grow. We think $1 trillion by 2030. That's all fine and good. But there are a lot of underlying challenges to do that, despite the demand. The demand, I think, you can justify the growth on demand, but this is a complex industry. Semicon West was this week, and the design conference was sort of parallel to that. One of these themes of Semicon was exactly this, right? What does it take to get the industry to grow to its $1 trillion forecast? But let's start with fabs. Start with foundries. We've talked about pieces of this before, but the way I'm thinking about this now comes down to the nature of competition within foundries, because essentially we could make an argument that we're on the cusp of a more competitive foundry environment than we have been in for, then call it the last 5 years, maybe even decade, where TSMC has largely had a big portion of the foundry lead. I mean, they are the dominant leader in foundry, north of 70% of manufacturing share. But Samsung's making good strides. We've talked a lot about Intel. You and I have spent time with Intel, understanding IFS and where that goes. They seem to be getting more competitive. There's process advancements that they're making. So, and again, right, for the first time, Intel is truly trying to operate like a foundry, which they hadn't before. So arguably there was two fabs. Now there's three, being a design services for outside parties. So let's talk about the competitive dynamics there. There's a lot that goes into process package. We've talked about how design is changing from chiplets to interconnects. We're on the cusp of backside power. All of this makes design like a super interesting new angle. But let's look at foundry competition. So how are we looking at the nature of the competition changing amongst those three fabs from what it was maybe 5 or 10 years ago?
So, I think the in my mind the biggest development lately has been Intel seems to really be showing progress in getting back onto the Moore's Law curve. 20A, 18A, they're on, as from everything they've said publicly, they're on track. Um, and I think that will be significant. That we've talked a lot. Intel still has a whole other bunch of challenges, but this is sort of the existential issue facing them, and it looks like they're on track to overcome that, which I think will be a huge for certainly for them. And then they have to get IFS up and running. But I think if they can get the first part solved, they'll have customers, right? They'll at least have people who will kick the tires and get it up and running. It's not going to change their financials in the near term. They
Mm.
still have to spend a whole bunch of money, but the fact that they're going to be competitive is going to be really, really important. And I think that's number one. Uh, Samsung, there were reports this week that Nvidia is going to move some GPU capacity to
Right,
Samsung.
right.
That's big news too. They've been very, very closely reliant on TSMC for years, so they're diversifying a little bit, largely because they just can't make enough GPUs. There's so much
Hmm.
demand. So that's it's a good validation for Samsung. Both Samsung and Intel, I think, are still you know meaningfully behind TSMC in
Yeah.
advanced process. but it's competitive in a way that it hasn't felt like in a few years. I don't know about 10
Right.
years. 10 years ago was a whole different world, but you
Yeah.
know, certainly 3 years ago, TSMC was the only one only game in town, and now there's clear signs of competitive vigor from the other two.
Yeah. I think the process point is an important one. We've talked a lot about sort of what does that look like in terms of, like you said, Moore's law curve moving down the process chain. Samsung's 5 and call it 4 nanometer process were okay, but not as good as TSMC's. I think there's a lot of hope that their 3 nanometer checks out. I think there was a report this week from Digitimes that said their yields are right now 50-ish% for 3 nanometer, but getting better. So bad, but on a forward progress track.
Yeah.
Everything we've heard from Intel in terms of their sampling of 20A, which is their 3 nanometer, sounds good. So there's actually going to be, TSMC will 100% be first because you're going to see Apple likely come out with 3 nanometer supply this year, and then more people come on it for next year. But the other fabs aren't that far along. But what I've always found was fascinating. It's hard to quantify this, but I'll give you one example, the only one that I'm aware of. But it's fascinating to compare the quality of process because I do think that's an important differentiator. And so, for example, I had said that Samsung's 5-ish 4 nanometer was not as competitive as TSMC's, and we actually had Qualcomm dual source a product that was on Samsung's process, and then they moved to TSMC's. And all these reviewers were all of a sudden saying, why is it better? Like, I'm getting better battery life. It's faster. And that was the first time you could sort of draw a line and say, on the merits of process, this one yielded a better product toward the end goals of performance per watt and efficiency and whatever. And I thought that was fascinating because, again, if we believe that Samsung, TSMC, and Intel will all be there in a similar timeline of a year to 18 months of 3 nanometer and 2 nanometer, then that's great. It presents all these options like you talked about. If I can't get enough, supply from TSMC, I can go to Samsung. But what if the performance of those products is very different? And I think that's a fascinating dynamic of the quality of process across these different foundries.
Yeah, it's interesting because we can't A/B test
Right.
semiconductor processes. Right? I actually get asked this question a lot by investors, like why doesn't Qualcomm just switch and negotiate prices by switching back and forth? Because it costs a lot of money and it takes a lot
Yeah.
of time to ramp up a second process.
Yep.
And I think just the lack of capacity at the leading edge, those constraints are forcing people to do this, to dual source. And I don't think that will become common because it's tens of millions of dollars to do that or more, but it is really, really fascinating. And I would argue it's not surprising. I think it's the results are what we would think they would be. TSMC is ahead, still considerably, but it'll be interesting to see what happens when Intel gets in the mix.
Mm-hmm.
I expect that they're going to be behind too, but
Yeah.
at least with 20A. But there's at least the possibility that they do what they say they're going to do, and they're going to overtake with 18A. So that'll be a very big change to the industry if Intel can get that more competitive.
Well, and the part that you hit on, I think, is interesting. I had a lot of conversations. I used to spend a lot of time back in the day with Broadcom's former CEO Scott McGregor, and we talked about this a lot. We talked about like, look, how do you really think about your roadmap for product when it comes to foundries? And he was always very fond of having what he called uh, uh, I'm blanking completely on the term, but basically portable libraries. So their libraries were portable. They built them in a way so that they could go to whatever fab they need. And Qualcomm similarly has had a strategy of being fab diverse, but as we point out, we saw for the first time some differences in quality. But if this plays out to where these are relatively equal, and I do think that's important, right? I do think that Gen Zero customers on a particularly new process need to be able to test this now and say, Is Intel's maybe better, or is TSMC's better? Like, I think that's an important part of how you're going to productize, because if I'm, if we're NVIDIA, for example, or if, let's use NVIDIA as an example, we can't get enough from TSMC, but we're going to have to use Samsung. Does that change what product of our roadmap we dedicate to TSMC? So, for example, do you put all the leading edge stuff on TSMC, and do you do trailing edge then at a secondary foundry, because that's where you're trying to get different economies of scale. It doesn't need to be as leading edge, and so are you, versus what I just say, well, I'm going to put the same leading edge product, H100s, right, or Apple A3 if they ever had to use Samsung, but or sorry, 3 nanometer if they ever had to do that. Would they just put the same product across those, or will they diversify portfolio, which is now a new complex decision that has to be made that wasn't there before?
Yeah, I mean, I'm thinking through my experience on the other side on the design side, and it is, I mean, it's significant because you have to dedicate a lot of engineering resources to adapt to the new process. And so typically companies don't want to do that. You design a product and you design it
Yeah,
for a specific process at a specific fab, and then you just let it run, right? And because that's, just from it's a, the design becomes pretty quickly fully depreciated, and then you have to spend more money to port it to a different fab is a complex decision. And I'm not convinced that the the big fabless companies have really thought through it all at a very serious strategic level. Right? I'm sure that all the big companies have somebody at a high level who's like trying to weigh, TSMC versus Samsung, or like, doesn't want to see a monopoly situation from TSMC.
sure.
But then you get down to the people who are actually doing the design and the business units who are like, I don't care about
Right,
big strategic
right.
issues. I have tactical problems, and like if you want me to port to this other process, give me another 100 engineers. So I think the it's going to require a little bit of rethinking and reorg at the fabless companies to really take advantage of this. But absolutely, it's going to be something that comes up more and more. Right now that
Yep,
you have, if we really have choices.
yep, yep. Well, back to the high level point. I would love, like your question, to be able to A/B test this more and look for more examples. We may not have them. Maybe we will, and I think that will be a fascinating part of this analysis. But that's one vector. Process is the other. Packaging is the other. That's starting to get talked a lot about. We've spent time on chiplets. There's no doubt that the industry is moving to a chiplet architecture, 3D stacking. The days of monolithic are likely over. It's only a matter of time, I feel like, before Apple moves to a chiplet model, and that'll be exciting for them and their design process. But chiplets aren't easy. It's the weirdest thing. Like, I've tried to ask people, how exactly do you mix and match processes from other foundries onto the same die? Like, it's mind blowing to me. I still have not had a good explanation of this, but Intel is a good example. They make some parts of their tiles with TSMC now, largely the GPU, possibly others. Then they come back and they put those on their process and on their products. Like, it's the weirdest thing to mix and match processes. But more and more companies might again take this approach, right? Just looking what we said about process. What if you can't get full capacity from Samsung or TSMC, and you can get some from Samsung, but you might mix Samsung and TSMC processes together, right? Somebody's got to package that. So we're in this now new competitive dynamic of packaging where I think Samsung is the most behind. Intel's making a big deal about this, about the UCIe forum consortium that they're on for chiplets. They really want to lead in packaging. In fact, Intel will tell you, right, as a part of IFS, they'll be more than happy if you want to make your stuff at TSMC and then we'll package your chiplets together. Like, that's a full-on service that they're happy to do. TSMC has that as well. Those are the two foundries really, really pushing hard on packaging. But that's another element of differentiation, right? People might want to mix and match process and nodes. And so now foundries have to have all of this now advanced technology, which is a whole nother set of materials and gear to do. But that's another now new part, right, of the competitive dynamic is packaging.
Yeah, unquestionably, packaging is super important. Like let's break that up because I think it's two things going on. There's packaging and there's chiplets, and the packaging side is getting very interesting. In part because some of the architectures that people are proposing for their chips require very very advanced packaging for this to work, and packaging historically has been somewhat of a low margin, capital intensive business, right? And it's done in sort of lower labor cost markets, Malaysia and China, right? The new processes that we're talking about for packaging are essentially semiconductor manufacturing processes and lend themselves much more to being done very close to the fab that produced the chip in the first place, right? And the capabilities of TSMC versus someone like Amkor or ASE are pretty stark. It's going to be very hard for the traditional packaging companies to compete at this level because it's a whole different manufacturing chain. It's absolutely essential for some applications, I think, for a lot of applications, and it's going to be a growingly significant. The significance of it will be growing when it comes to differentiating among the foundries, and it's fun from a technical perspective. It's super fun. It's really going to allow us to do some interesting things. But separate from that is chiplets. I think chiplets are really complex and amongst themselves. It's a whole sort of order of magnitude increase in complexity of the designs. I think the vision you're talking about, where you're mixing and matching process foundries, I think we're still a little ways away from that, right? Because certainly if you talk to investors, they get they get more than a little bit ahead of themselves when you look at the industry. Because I've talked to people and read some reports who say, oh, you're going to take, a chiplet from this company and one block from one company, one block from another company, and you're going to all mix them all together, and it's just like maybe someday, but today it's AMD is doing chiplets, and they do everything themselves. They do all the design themselves. They get it all from TSMC, and then they package it all together. Once you start like mixing and matching like that, it gets even more complex to design.
Mm-hmm.
And so I think that's gonna take a while, right? As you know, I personally I think Apple. I'm not sure Apple is in a big hurry to do chiplets. I think they may be forced to, but I don't think they really
Right.
want to. I think they'd rather do
Right.
it monolithic, because mixing and matching like that is going to be kind of painful. There's still a lot of like low level technical things that have to get sorted out to really get this to
Yeah.
work.
Yeah.
So I'm a little bit more. I think chiplets are going to take a little longer, but the broader topic of packaging is really important, and I think
Right.
there's a lot of interest I know among VCs in packaging now, which is mind-boggling to me because it's not
Hmm.
something they ever really wanted to touch before or in a long
Hmm.
time. And I've had a few discussions with VCs on this subject this year, as they're starting to look at it, because I think there is the potential for a new entrant here, someone to come in and use a semiconductor manufacturing process to do some advanced packaging. It's pretty expensive, but I think it's feasible that we could have a new entrant in here, sort of shake things up a little bit.
Hmm. Well, the part that chiplets that I think about, and I guess the point you made, I think, is one of the more interesting then to debate, which is a is this are you forced to do this by nature of some of these limitations that we're talking about? Meaning, I can't get a tile, or I can't get what I need on leading edge, so I'm going to do that on a trailing edge, and I'm going to do that from another foundry. It might not have been my preference, but it was what I was forced to do. I think that's an interesting discussion for this, because I'll just use an example, right? Intel is making their GPU tiles on TSMC, and to some degree, that's because you could argue that TSMC's was a much more mature process for GPUs because they've been doing it than Intel. So that was the right decision. But was that Intel's preference? If Intel Foundry and this is on a later node. It's not on an even or on a leading edge node. Had they had the ability internally to do that on their own, and they probably will at some point, and then they'll do this, like would that have been their preference? And then your Apple example is another one. I think if it was either you and I were talking about this off the air or something else, what if they cannot figure out the modem? And then they just go, well, let's work with Qualcomm or MediaTek or somebody, and let's just put the modem tile. Let's just take their modem tile and put it on our SoC because we want it on the SoC, and that's the only way we're going to be able to do it. You're right, not their preference, but an option should all parties be willing to. So I think meta point, it's interesting to me is whether that's the best way to go or whether that's the way they have to go for design. And I think that's an important, at least an interesting discussion point.
Yeah, I mean, we start to get into some of these issues. It's hard on the outside to really debate it because in my mind, I'm not sure Apple gets. I'm not sure how much advantage Apple ultimately gets by packaging the modem as a chiplet, as opposed to just having it as another die,
SIN modem, yeah,
closely connected. And absolutely, there'll be some cases where it makes a big difference, and others where you don't need to go down that very complicated path to get there. But I think it also, I think part of the debate you and I are having, and it stems from sort of a broader topic, which is capacity, right? I think if we really have three leading edge foundries, we're going to be in a very different capacity environment than we're today. Like I think a lot of our conversations have been premised on this idea that we're in a constrained capacity world. If we have three foundries at the leading or close to the leading edge, then we may not have the same capacity problems we have today. And I think that's a broader topic on the industry. Something come out of Semicon is not just at the leading edge, but at the trailing edge, where we've been very capacity constrained for 3 or 4 years. That's changing. I think most people in trailing edge land are much more worried about overcapacity than undercapacity right now. And so it will be a very different world when we have excess capacity at all nodes, which I think is going to come. And so I think that sort of takes away some of the motivation from moving to really crazy chiplet stuff.
Right. No, that's a good point. Keep in the back of our minds for future. So the other part I thought was interesting in terms of competition was a point that was made on Twitter by a person that we sort of both follow, Doug O'Loughlin from Fabricated Knowledge, that basically he had, and I think they had seen this at Semicon, that 100K wafer starts is a terawatt hour per year. That's equivalent to a town of 100,000 people. And what that got me thinking of was when we think about this idea of scarcity, right? So like what's scarce that certain assets, in this case foundries or others, have access to that others don't, which put them in a strong position to compete, is power. And even though this isn't a foundry point, that same point is relevant for, just for example, your hyperscalers. There are only 3 hyperscalers, really maybe only 2, who can actually acquire power on the grid. Like they almost have a monopoly on the grid against their competition in order to deliver the necessary kilowatts per hour for a data center. And the same is true with foundries, right? There's limited power. Foundries take a gigantic amount of power to make, but we're up against that, right? So I use that to say, and going back to your point about excess capacity, like even if we could move up to, like, even if TSMC could move to 400,000 wafers a month, 500,000 wafers, do they have the power to do so? Like, I don't know.
Yeah, it's a big concern. I think. I mean, you look at the stats for how much power TSMC consumes every year, and I mean it's a major portion of Taiwan's electrical grid, and I've also, like I've been doing a lot of work on data centers lately, the physical construction of the plant, not just the chips, but how do you build a data center, and that's the it's not just that you're constrained in like designing your data center to optimize compute versus how much power you have. You beyond the power budget. It's just a simple question of can we even get electricity to the site,
Yes.
right?
Yep.
And Northern Virginia, which is the the epicenter of so much of the cloud, is out of electricity. Right? There's you can't get any more. You can't build any more data centers in Northern Virginia because there's not enough power, and so it's a big problem. I'm not quite sure. Everybody's building big fabs in Arizona right now, which is uh, which has a lot of hydropower, which is in good shape at the moment, but a year ago I think was a bigger concern,
Yep.
right, with drought conditions. So
Yep.
power is a big part of all this, and we're bumping up against limits in some places.
Yeah. Well, and think about just this point about foundries and competition, where Samsung's largest US fab is in Texas, and you constantly hear people in Texas complain about, oh, our power's been down for 10 days because, we're the grid can't handle all of our air conditioning. Like they already don't have it, and you've got one of the largest foundries where grid is already a problem in Texas.
Yeah,
So, yeah,
we're gonna
that's a
start move.
fascinating one.
We're gonna start moving fabs to next to giant hydro plants.
Hydro plants and something that can do it. And people genuinely ask this question, like, should Taiwan or we have this debate here too, like, should we start investing right in nuclear again somewhere near one of these plants, even if it's on a minor scale, just to help power? Like, but that's like a 10-year process to build these things. Like, you got to solve these problems now. But that's why I bring this, I spotlight this point, just going back to what we're saying, is that the growth is up against just some limits that to some degree are outside of our control, and just we want more of these things. Like, demand being there are just physical limitations, and in this case, it's electricity. Well, and to your point, if we're also fighting the hyperscalers, like, where are we going to get all this power?
So let me get straight. It's nuclear power plus microchips plus 5G. It's like the conspiracy nexus all in one spot.
We would blow it up. America would not survive. It would splinter into all of its factions at that point. Yeah, challenging. Okay, so the other part, scarcity, we mentioned, what that you brought up was the materials. So I've talked to a couple of investors about this. Right, they're categorizing this as forever chemicals, and the possible restrictions on forever chemicals feels significant. I think nobody's kind of worked out what the true implications of that is. The reality is there are no substitutes. Like, people were like, well, could they come up with substitutes? No, they can't. If this was fully restricted, that does have drastic implications, especially if they said you in the United States you're not getting them. Okay, well then what does Intel do? Right? There's parts of this that's a process, but we don't fully know how that shakes out. So I don't know what you've heard, but I know this is top of mind to everybody as at least a high level concern to be aware of.
Yeah, I mean there were a lot of these companies at Semicon talking about people who supply the machines that apply the chemicals that are in question here, and I, it's a real problem. I think there is. I don't think anyone has a solution, but I think there is some hope because I don't know if you remember a few years ago the big concern around fabs was water, wasn't enough
Yep.
water,
Still
and
is. Yeah.
it's still a problem. But there was a lot of good engineering went into it, and you have conditions like in Arizona, Intel is basically a zero consumer, a net zero consumer of water. Right? They take an amount of water and they give it all back in cleaner condition than it came in. Right? They have these big filtration systems now. It's we still need a lot of water for these things, but they found a way to greatly reduce the impact through good engineering, and hopefully they'll be able to do something like that with these forever chemicals. I agree. I don't think there's an easy replacement, but maybe there is the ability to limit their to I don't know. I don't want to get into it because I don't know if you can reuse it, but there's some technical way that we can at least limit its spread, keep it contained,
Yeah.
neutralize it somehow. I think but it's gonna take years. Yeah, it's gonna take a few years to sort it all out.
Make peace with China, maybe.
All for
Sorry
it.
for being such a contrarian. On our inability, or politicians' inability to recognize how globally interlinked one of the most important parts of technology innovation is a great one. Um, okay, well, that more to be said on that, but I think everybody that listens is top of mind. But at least that's something to keep an eye on. There's a concern, but not terribly sure. But again, that's a natural resources is a constraint, right? We're up against, so that's one of those factors as well, inhibiting the potential growth. Um, so let's touch on the last one, which is design.
Wait,
But
before we get there, because there's another angle to this. I think is you almost segued into, which was if we're talking, it's other inputs beyond just chemicals. It's materials, which is very much in the
materials,
news this week because China is restricting exports of gallium and germanium, which are
yeah,
both important components of wafers and substrates for certain applications, right? And I think this. I mean, this topic is wonderful because it just sort of encapsulates everything we've been talking about. You have fairly limited supply, fairly toxic to
material,
produce
yeah,
these things,
yeah,
and right. I mean, gallium is typically it's gas, gallium arsenide. So there's like all kinds of toxic stuff involved in the use of gallium in semiconductors, and then you have geopolitics on top of that, which is right. I was walking the show floor the other day uh, with a friend of mine who had actually bumped into the China germanium sales team who was at the show. Right, it was Jordan Snyder from the China Talk podcast, and so he saw these guys, and like we're just like we felt so much sympathy for them because you come all this way, you're planning this trade conference visit for months, and you get there, and like the week before, you're like, oh,
yeah,
sorry, I can't
yeah.
sell you anything.
How's your sales guys going? How's it going? What an opener, right?
That's right.
How's sales this week? Hitting your quota?
I mean, full credit to them for actually showing up at the show. If I
Yeah,
had been in their shoes, I would have just stayed at the hotel
yeah,
bar all week.
right.
But but it is interesting. I think. I mean, we don't have to get into all the politics in China behind this, but it just seems this seems like a pretty futile attempt. Not quite sure why the Chinese government did it. They tried restricting rare earth imports a few years ago
Right.
during the Trump
Right.
trade wars, and that just led to people opening up rare earth mines in other parts of the world. And I think the same thing is going to happen here. It seems it's very this is kind of counterproductive, and I think it's one of those things that we'll forget about in a few months because it just is going to have very little impact. But it just is a reminder that this whole supply chain is super complicated and super interconnected,
Yeah.
right? And it's there are going to be other things I'm sure we'll stumble across in months ahead that are like, oh, those go into semiconductors.
Right. Exactly. Okay, so that was the resources materials bits. So let's bookend it with design. And one of the things that the precursor to that I'm intrigued with is a topic came out of the show about talent. You know, what will design or semiconductor engineering look like in the future? How are we attracting new talent? And in this case, I sort of say U.S. talent. So like our swarms of kids, now adults going into college to become semiconductor, engineers. I know part of this CHIPS Act is designed to bring R&D back to institutions. I don't know if that will happen, but that's kind of the idea of can we facilitate more talent? But that's an important part, right? Where will design be in 10 or 15 years? We need new crops of designers coming in and doing that. And how do we do that? Maybe it's not as big of a problem as I'm thinking about, but it was highlighted at the show. So let's start with talent, and then we can go more into the design rabbit hole.
So a month or two ago, I briefed the CHIPS Act team at Commerce. I just got on a call, a Zoom with them, and mostly we were talking about China. I was telling them like how where China stands with semis and what they do well and not so well. But towards the end, they asked me. We were sort of thinking bigger, right? Because what's the CHIPS Act,
Right.
where the fund's going to go to?
Right.
And I had a few sort of crazy ideas, and they said, well, what about talent? And that actually like that was a big topic. We spent a lot of time talking about that because they were very concerned on that topic. Do we have enough? Do we have a well trained labor force in the U.S. to actually put some of their policies in place? And
Right.
they seem somewhat anxious about it. I think we'll overcome it, but I definitely think it's a good concern, right? Because to your point, like kids going into college today, they're not thinking about going into material science and semiconductor engineering.
Right.
They want to go into computer science and write software
Yep.
and
Yep. Well, and even those, like, there's a bunch of my daughters are, high school, college age, and I've asked this of sort of their friends who are going into engineering or want to be double E's, and for them, it's actually more things like robotics, and parts of like physical engineering, not semiconductor engineering. So I agree that's an interesting point. I would love more context on this, like how big of a problem are we at? How do colleges think about this? Because you and I had a conversation this week that we can't necessarily talk about, but one that I thought a lot about, which is okay, what architecture will these kids start experimenting with? Like, let's just say that you and I, right, we're going into to semiconductor design or engineering, and this was one of them. My guess is it's going to be RISC-V because it's free, and my college probably has I would imagine, foundations for me to start messing around with some RISC-V design. Right? They may not have a license from somebody else. It's certainly, probably not going to be x86. So if you use this idea of, I would just say, what would the equivalent of Arduino be for potential future semiconductor engineers, I would venture a guess RISC-V is perhaps best positioned to do that, assuming that this CHIPS Act money does what it does and institutions use that for R&D, and in this case I say colleges. RISC-V seems like a natural architecture that they start playing around with.
it's an interesting topic in a way that I don't think it ever has been before because the ability to actually design and get a chip built is fairly easy right now, right? I remember when I was in school, I had a friend who was an electrical engineer, and he was like really fascinated. Like they had some kind of mini fab on campus, and like he knew his senior year he would actually get to build something, and that was a
Mm,
really big deal, and it was
mm,
right. But now you can sign up. Google and Skywave and Global Foundries all have free shuttle programs where it doesn't take much. You use their design tools, and you get a wafer back, which is
yep.
like mind blowing to me. Like for little or no cost, you can actually just any college student can go design a chip now in a way that was I don't think has ever been truly possible before. And you're right. Like, how are you gonna I'm pretty sure there are ARM academic licenses which are a little bit freer, but still, like, if you really want to muck about in the deep level mechanics of it, RISC-V is a good place to start.
Yep.
And
Yep.
so,
Agree. So that's the talent part. Um, some of the design components that we talked about. What I guess what are the challenges and or opportunities then specific around design? I mean, you said you went to DAC a bit. I saw some tweets from it. What were some of the takeaways around around
yeah. So
design?
so next to Semicon, which is a materials and manufacturing show, there's the Design and Automation Conference, DAC, which has historically been about IP libraries and EDA tools. And
Mm,
this is a show that is not recovered from the pandemic.
right.
Right? I was
Right.
on the show floor, and uh, one of I think Keysight, the testing company, had a booth, not a big booth, just a normal sized booth, and they had jugglers performing in the booth. And I'm pretty sure every attendee on the show floor was at the Keysight booth watching the jugglers. They were pretty entertaining. and then there was nobody else on the floor except for people standing their exhibits, wishing they could go watch the jugglers. It was a ghost town. Like everybody used that word ghost town. And so part of that I think is a reflection of the organization behind DAC. They need to rethink that show. Uh, but it was also, it was weird to me because I actually think IP issues are becoming much more interesting
Yeah,
and much more relevant.
for
Right?
sure.
If you're gonna, if not everybody is gonna be able to tape out a 2 nanometer chip. I mean, it's gonna cost $100 million at least to do that. And so there are lots of companies out there who are gonna go down the IP path, right? And similarly, if you're designing a 2 nanometer chip that's already expensive enough, do you want to recreate the wheel when you can get IP from other companies?
Right, right.
But that was not really reflected at the show floor. I think there's a lot of different avenues that need to get explored here, and it wasn't on display at this show. I mean, it's another subject I've been doing a lot of work around is IP for AI chips. I think that's a big
Mm-hmm.
issue, right? And I
Yeah.
think and I mean the other one I've been trying to figure out is IP for analog companies, right? And that's another area that seems promising, but needs some real rethinking on how people operate. And I would have been happier if there was something more interesting to see at DAC, but it wasn't on display this year,
Yeah.
and so
Yeah, but I mean, I agree with your overall premise, right? Those are important parts of the broad semiconductor industry. There are a lot of companies who do and put a lot of R&D into licensing and actually make it very easy for companies to innovate and use those technologies and get time to market quicker, things that they just don't need to do themselves. So it's not an unimportant topic. It's really important. I think it's just you're right. It's tough the way the show was framed. There's probably some other ways you could go about that. It doesn't feel as sexy as a topic as other things, but from a fundamental point of importance to the industry, it's not trivial.
yep, agreed.
All right, so we've covered a lot of ground on the opportunities, challenges, and whatnots for the growth of the semiconductor industry. I think that was a good dive. I think we'll button it up there. Um, Appreciate everybody listening, and as Jay constantly says at the end, that I should always remember. Please like our podcasts, tell others to subscribe, give us a nice review, thumbs up on iTunes or whatever. It helps the show keep growing. We appreciate everybody's support.
Thank you, everybody.